this for some x, right? So if there is x, then it's called quadratic residue, right? If x exists, right? If it doesn't, then it is called quadratic non-residue. And we are not very interested in finding x itself. We are more interested in checking whether it's residue or not. So in some sense, the whole chapter is dedicated to the determination of this classification, whether it's quadratic residue or not. So this is the goal. And very important breakthrough happened with Euler's idea. And last time I gave Euler's criterion. If this number a to the power of half, right? I call this half, is congruent to 1, then it's residue, right? If it's not, then it's non-residue. And if it's not quadratic non-residue, what about a to the power of half? Will it be very different? In fact, it's not very different or very far away. If it's non-residue, this value will be equal to -1. So up to this point, I covered. Any questions up to this point? So we don't practically use this to calculate whether it's quadratic residue or not, because this requires powering, right? This thing is not easy. So we want to focus on theory on top of it. Theory on top of it. So symbol is called Legendre symbol. Legendre symbol says if A is quadratic residue modulo P, then we say it's 1. If it's not, then it's -1, right? So if A is non-zero number, then A over P with parentheses equals 1 is not a fraction. This is not a fraction, but we say A over P, or Legendre symbol A with B and P, and then if it's 1 is quadratic residue. So as you can see, here we have the value 1, and then here we have the value 1. If it's non-residue, here we have value -1, and then you have value -1 if it's quadratic non-residue. So in this sense, we can develop theory about this symbol using the Euler criterion developed here. So this is what I will do today. In other words, suddenly, on top of this, we begin to build theory after theory. In the end, we'll develop amazing property called the quadratic reciprocity. And by using quadratic reciprocity, we can reverse these values to calculate the result faster. Why care? Because this result determines whether the solution exists or not. And this existence guarantees some solution to more complicated problems. So if the solution to this exists, then this becomes 1, then this symbol shows 1. If it doesn't, then -1. So 1 is good, -1 is bad, right? Any questions up to this point? Then today we will develop theories on top of this relation. In other words, in essence, the symbol A over P with this Legendre symbol is congruent to A to the power of P minus 1 over 2 by definition. In the first place, people didn't develop this way, but it had the same result. Then on top of it, what kind of things can you develop? First of all, very easy thing. Assume that we have 1. Something squared equals 1. Will it have a solution? Something squared equals 1. Will it have a solution? What could be the solution? 1 or -1 is the solution, right? So if it is, so always remember the definition. If the solution to this problem exists for 1, then it is called quadratic residue. 1 is quadratic residue, right? Because 1 squared is 1, so solution exists. right? 1 squared is 1. And because solution exists is 1. But at the same time, if you use this, how can I prove this? Use this. Then 1 to the power of half. 1 to the, if you multiply 1 many times, it is still 1, right? So it is congruent to 1, right? So it is 1. If you don't understand, you can ask me. I'm giving you trivial case. But now it could be a little bit harder. So I will follow the text so that you can later review these theorems. Assume that A is congruent to B. Then, as you can see, x squared equals A is the same as x squared equals B, right? In other words, the same problem. So if solution exists, then solution to this exists, and vice versa, right? If solution to this exists, then solution to this exists, right? Vice versa. And what if A squared is given? So this is the property number A. It is 9.2, right? Theorem 9.2, property A. And then property B. If we have A squared in the top position, right? If we have A squared in this top position, then we can rewrite the problem this way. Oh, it is the same as saying x squared is congruent to A squared. Then can you find the solution to this problem? What could be the easiest solution? A, right? A squared is A squared. So if A squared is given, then it is 1. It's also trivial. Or if you want to use Euler criterion, then you can use Euler criterion. A squared is the top portion to the power of half. Top portion to the power of half, and this value are congruent, right? By the property that I mentioned, right? This top portion to the power of half and this Legendre symbol are congruent, then this is equal to a to the power of p minus 1. And by Fermat's little theorem, this is congruent to 1, right? Fermat, right? Very important property. And then it's 1. In some sense, if you need to remember just one thing after taking number theory, that is what? This term, right? Just one thing, then this is it. And if you don't have a question, I will continue. If you have a question, ask me. Then the third one is A over P, and then this one that I already used, right? Already used. And fourth one is AB over P. What is your guess? What can happen? A times B is in the upper position. Then what can happen? We can split it, A and B, right? A, B is here, and we can split, and then all others follow. This is the summary of many cases. For instance, A is a quadratic residue, and B is a quadratic residue. Then what about A times B? Will A times B a quadratic residue? So quadratic residue, then it should be quadratic residue. Either one is residue, the other is not residue, then what happens? One is residue, the other is not. Then what happens? A times B is not residue or non-residue, quadratic non-residue. Or both are not quadratic residues, then what can happen? A times B is quadratic residue. So this property is the abbreviation. Then how can you prove it? Use this property. So let's do it. ABP equals, by the above property, this, right? Do you follow me or not? By the above property. And this power splits, right? This power splits. Then it is the same as saying this. And by the property C, this is the same as A over P in Legendre symbol. This is the same as B over P in Legendre symbol. And done, right? So as you can see, suddenly abstract thing abstract properties are being built, right? Suddenly, up to about this point, people might be confused, right? Suddenly, it's not that trivial. But why can we go through this so easy? Because we developed something that can be called a breakthrough, right? Breakthrough is what? Euler's criterion, right? Euler's criterion is the breakthrough. If it's the residue, then a to the power of half is 1. If it's not, then negative 1. This is the breakthrough. Because of this breakthrough, we can suddenly develop this kind of property very easy. In other words, someone may ask you, oh, we have two quadratic non-residues and we multiply, then what happens? Then you can easily say that it is a quadratic residue. Why? Because of the Euler's, right? Euler's criterion, right? Unless you stop me, I will continue, but if you have confusion, ask me. Then the next property is minus 1. So what happens to this? If it is 1, always exists, right? 1 is 1 squared, so it is easy. But what if we have negative 1? Then we can rely on Euler's criterion. Euler's criterion says it is this number, right? A to the power of what? Half. Do you follow me? Property C is very important in this section, right? Property C is very important in this section. Negative 1 over P is negative 1 or A to the power of P minus 1. Then let's check. If P is an odd prime, right? Or we are considering this for all odd prime, right? Odd prime P. Always we consider this for odd prime P because if it's an even prime, it's very trivial. The problem is very trivial. If it's even prime, then it's just 2. Other than 0, 2 has only one entry, there is 1. We don't need to even waste any time on even prime. So when it's an odd prime, P could be, for instance, P could be what kind of type? 4K plus 1 type or 4K minus 1 type or plus 3 type, right? There are two possible types. It cannot be even, right? P cannot be even, so P should be odd. Then if we divide it by 4, then it is 4K plus 1 and 4K plus 4. If it is 4K plus 1, then this power can be easily written minus 1 to the power of 4K plus 1 minus 1. Then it is equal to minus 1 to the power of 4K plus 1 minus 1 over 2, 2K. And then it is multiplied 2 even times, it is 1. So if it is 4K plus 1 type, it's trivial. If it is 4K plus 4K minus 1 or 4K plus 3 type, then this, oh, I wrote this, then you might be confused, so I will say minus 1 to the power of this equals, right? And then the same property, minus 1 to the power of P minus 1 over 2 becomes negative 1, and then 4K plus 1, 4K minus 1 minus 1, right? 4K minus 1 minus 1. So 4K minus 1 minus 1. So as you can see, it is minus 1 to the power of 4K over 2, and then minus 1 to the power of negative 1. Do you see it? Right? 4K over 2, and then minus 1 divided by 2, so it is negative 1. Then, as you can see, this is even number, even power 1, and then minus 1 power is 1 over negative 1, right? 1 over negative is negative 1, so it is negative 1. So, as you can see, it depends on P. If P is 4K plus 1 type, it is quadratic residue. If it is 4K minus 1 type, it is quadratic non-residue. It depends on type. And in fact, we proved this before using Wilson's theorem. In Wilson's theorem, I said, just after Wilson's theorem, I said x squared plus 1 has a solution if and only if mod P, right? Only if P is congruent 4K plus 1, right? 4K plus 1 type, right? 4K plus 1 type. If it is not 4k plus 1 type, then solution does not exist. So I already mentioned this before. If we rewrite this, then we can get -1, right? So this is exactly the situation. We are solving x squared is -1. And when does it have a solution? When p is 4k plus 1 type. When it is 4k minus 1 type or different type than this, then solution does not exist. So this was mentioned right after Wilson's theorem. So I proved it before, but now we're using Euler's criterion. We can have a natural proof. Any questions? So take a look. We now know many properties. When it's 1, we know trivial, right? When it's squared, it's very trivial, already done, right? When it's -1, we can classify. And then when it is like multiple, then we can just break up. Done. Any questions? Then using this, we can develop many cases. And the text asks us to calculate the possibility of solving this. First of all, when you are asked to solve this type of problem, you can use smaller top portion, because if you have big one, then it's difficult to decompose, right? Use smaller portion using property number 1. What is the property number 1? I mean, let's go back to the text style list. This, right? This. When you have A and B, then we can always use the congruence. So -46 o'clock is the same as 1 o'clock. Between 0 and 17, -46 o'clock is the same as 1 o'clock. Fast. So I am not that fast, so let's divide. 46 divided by 17 gives us 3, then 51, then subtraction gives us -5, right? So -5, so it is 5 o'clock, because we already have negative is positive. So we got this. So we can simplify and investigate this type of thing. Or you can break this up if you like. For instance, there are many ways of solving it. Another way is you can break this up to this, right? By property. It's very inconvenient to use text. So I will name properties. For instance, let's call this congruence property, right? Congruence property. And let's call this square property. And let's call this product property. And this is Euler criterion, right? Then it's easier to remember, right? Take a look. I will call this congruence property. I will call this square property. I will call this Euler property. I will call this product property. Any questions? Just easier to describe. It's descriptive. Instead of A, B, C, I will say by congruence property, square property, Euler property, and so on. So by product property, did I say product? Yeah, product property. Product property. By the product property, we can break this up. So 46 is -1 times, 2 times, and then 23, right? And then 23 o'clock by congruence property. 23 o'clock is the same as what o'clock? 6 o'clock, right? 6 o'clock. And then 6 by the product property, 2 times 3. And we have 2 squared here. then by the square property, it is 1, right? So we can get this kind of result, right? And by the previous result, when this prime is 4k plus 1 type, then this is quadratic residue. It is 4k plus 1 type, 16 plus 1. 16 plus 1 is 17, so it is 1 by the previous result, and then 3 is 17. So in any case, we end up with smaller number over the given number. So if we solve either 5 over 17 or 3 over 17, then we are done. Yes?
Why did the negative 1 over 17 become 1?
It is by the previous property that we proved upstairs, right here. It's 4k plus 1, and this is 1. 17, the prime is 17, right? 17 is 16 plus 1 because of this reason. So always, when you have negative 1 and something, look at the denominator. It's not exactly the denominator, but it's easier to describe, right? Or the term underneath, right? Any questions? Then the next one that I want to do is showing other examples, and later I will return back to the way to calculate 5 over 17 or 3 over 17 using quadratic reciprocity. Of course, right here, if you have a computer or you can do the binary exponentiation, you can finish it. How? This is congruent to what? 5 to the power of half, right? 5 to the power of half, right? 5 to the power of half can handle it. But this requires binary exponentiation. That is too tedious, so I don't want to go into this direction. Even with 3, we can use binary exponentiation, 3 to the half, right? And then we can get the value to answer. I will use computer algebra system to show you, but in any case, these are not easy until we have covered the quadratic reciprocity. So let's calculate it. Power mod 3 to the power of 17 minus 1 over 2 with modulus 17, right? With modulus 17, right? With modulus 17. So it is negative 1. It's quadratic non-residue, right? 16 o'clock is negative 1 o'clock, so it's negative 1, quadratic non-residue. What about 5? So it's still quadratic non-residue, right? 5 or 3 are both quadratic non-residue, and we get negative 1. It's not 1. So by this result, we can get the conclusion that this is quadratic non-residue. Not by hand calculation. Of course, it's not actually impossible to do it, but it's tedious, right? This is not impossible to do, but it's tedious. So because of this reason, negative 46 is quadratic non-residue. Any questions? Then, as you can see, still difficult to determine. So our ultimate goal is quadratic reciprocity. With quadratic reciprocity, what can we do? With I will introduce quadratic reciprocity, even though it is not the time, but assume that we have two prime numbers which are relatively prime. Right, two distinct prime numbers are the prime numbers. Then we can calculate this kind of reciprocity by using the reciprocal with minus 1 to the power of, I just used the boxes before, but I will say that half of first prime, half of second prime, right? Half doesn't mean exactly half, but about half, right? So this is the property. Then I will show you why this is so convenient. Take a look. We had 3 over 17, right? It's not easy to calculate it. So we consider the reversed one, right? And then minus 1 to the power of 17 minus 1, 3 minus 1. Then 17 minus 1 is 16. 16 over 2 is 8. So negative 1 to the power of 8 is 1. So this is, you can ignore this. Then what happens? 17 o'clock is the same as minus 1 o'clock, right? Minus 1 o'clock. Then take a look. When you see minus sign, always look at this portion. Always look at this portion. And what about this portion? Is it 4k plus 1 type or 4k minus 1 type? 4k minus 1 type, and minus 1 is bad, right? So this means negative 1, right? So as you can see, quadratic reciprocity makes the calculation way easier. You don't even have to do any binary exponentiation once you arrive at quadratic reciprocity. And let's use 5. If it's 5, then 5, 17, then by quadratic reciprocity, 17, 5, and then minus 1, and then 17 minus 1, 5 minus 1, and it's plus. Then with this, we can have this result, 3 over 5, right? 2 over 5. Do you understand what I did or not? If you don't, then I will explain the reason. So this is by the quadratic reciprocity, and then this is 1. So you can ignore 17, 5 by congruence property. 17 o'clock is the same as 2 o'clock with 5-hour system, right? With 5-hour system, it's the same as 2 o'clock. Then now this is congruent to 2 to the power of half, right? Half. 2 to the power of half is very easy to handle. 2 to the power of half is 2 to the power of 2, 4, right? 4. 4 is congruent to what? With mod 5. 4 is congruent to negative 1 with mod 5, right? Mod 5. So it's congruent to 1 with mod 5, right? Because of this, it is negative 1, right? Because of this, this is negative 1. In other words, once we reach this ultimate goal of this chapter, then we can easily calculate almost any Legendre symbol values. So you may pick any 2 prime numbers to show you. You may pick any size 2 prime numbers, then I will show you how easy it is. I only use computer algebra system to check whether what you chose is a prime or not. So pick any 2 prime, or I can show you possible prime numbers. 911. So is prime 911. 911 is a prime. So you chose 911, and please pick bigger number than 911 at the bottom. So let's try something. 2,903. So it's prime, right? 2,903. So assume that you are asked to check whether 911 is a quadratic residue with modulus 2,903. It's almost impossible by hand calculation, right? I don't mind if you can really do the hand calculation of this, or using first 1 square, 2 square, 3 square, up to like 2902, right? I don't mind to see that kind of result. but it's very inefficient. Then we can use quadratic reciprocity, 2903, 911, and then negative 1 to the power of 911 minus 1 multiplied by 2903 minus 1. And as you can see, if you look at it, then it is 910. The 910 divided by 2 is odd. And then if you see the second number, 2903 minus 1 is 2902. 2 divided by 2 is 1, so it's odd. So both are odd, odd multiplied by odd. So this result is this result multiplied by 1. Do you see it? So it's very easy to calculate the power. Then now you use the congruence rule, congruence property. By the congruence property, what can you do? 2903 is congruent what? So to do it, we can divide it by 911, and about 3 will work, right? 3 will work. So we use 3 then. 3, 3, 2, 7. If you subtract 0, then this subtraction gives us 7, 1, right? 1, 7, 0, 9, 1, 1. Then we can break this up. We can break this up so that we can have 2, 5. So by the product property, we can break up 170. So take a look. 170. 170 is 2 multiplied by, is equal to 2 multiplied by 85, right? Do you see? 2 multiplied by 85. 85 is 5 multiplied by 17, right? So we broke this up. So let's break this up. Then by the product property it is 2 over 911, and then 5 over 911, and then 17 over 911. So we can use the product property. I'm showing you the properties. So please check whether you completely understand up to this point or not, other than the big theorem called quadratic reciprocity. Then later we will develop the theorem for 2. So this will be developed very soon. And then 5, what can you do? You can apply quadratic reciprocity, right? You can apply quadratic reciprocity so that 911 over 5 is used. Do you see it? And then minus 1 to the power of half. Then it is 1, right? So you can have 1. And then we can 911 over 17. Then power, and then negative 1. And then this power gives us 1. It's very trivial to calculate. Suddenly, as you can see, there is 2 of this, and then this. Then you may wonder, oh, what happened to 2? So we will focus on 2 right after this explanation. And once you know about 2, then you can easily determine whether it's residue or not, depending on this number, right? 2 is fixed, then depending on this number. Sometimes residue, sometimes not. And now we can focus on this part by using congruence rule. So this number multiplied by 1 over 5. Do you see it? By congruence rule. 1 o'clock is the same as 901 1 o'clock, right? 911 o'clock. And 911 o'clock with 17 is what? So I will use this portion. 911 over 17 is about 7 is too much. 6 is still too much. 5, right? Then 85 subtracted, then 61. About 3, right? Then 50, right? Then it is 10. Excuse me?
The minus 1 is still there too, right?
Before you broke up 1.
Oh, yeah. Just a moment. That's true. Negative. Thank you. Yes, I should have carried all those. Yes, so in any case, we arrive at this point. Now, we have one more 2, so I will write it in the next column. So, equals, I will write all the involved terms, 2 over 911, and then 2 over, as you can see this, right? You have 2 times 5, right? 2 over 17. 2 over 17, and then 5 over 17, and 1 over something is already 1, right? 1 over something is always 1. So we wrote it, and if you don't understand, you can ask me. Then finally, 5 over 17. So I will not carry this all the way down. I will just calculate this straightforward. Then, by the reciprocity, 17 over 5, right? And then, minus 1 to the power of half, that will be even, right? And then, because of the 2 over 5, right? Because 2 over 5, it is congruent to 2 to the power of half, mod 5, right? Mod 5, then it is 4 o'clock, then it is negative 1, mod 5, right? So, this is negative 1. So negative are all gone, then it only has this portion. So once we can handle 2 over something, we are done, right? So I will cover 2 over something very soon. But in any case, as you can see, I didn't use computer, I didn't use any calculator, I just used by simple addition, subtraction, or division, or multiplication, and rules. So please check whether you completely follow up to this point or not.
I guess I'm lost. I don't know where you get the 2 over 17 and 5.
2 times 5 is 10. Do you remember 10? By the product property, 10. 1 over 5 is always 1, right? This thing is 1, right? This portion is 1. 10 over 17 is 2 times 5. 10 is 2 times 5. By the product property, we can split this into 2. Any other questions? So you can use rules to calculate the value. So what is the point? To find whether the solution exists or not, we need to calculate the Legendre symbol. But to calculate the Legendre symbol, you don't have to use the definition. You can use the superior rule, right? You can use all the rules that has been developed to calculate it. Only thing that I didn't mention is this portion. And in fact, when it has this kind of number, generally, when you have 2 to the power of 2 over p, then it is equal to negative 1 to the power of p squared minus 1 over 8. This is the case that we will prove very soon. So with this, we can calculate 2 over 911, and then we can calculate 2 over 17, the Legendre symbol, and then calculate the result. So to do it, all you need is whether this number, after divide by 8, has some number, right? So if you divide 911 by 8, then what do you get? And 1, 8, right? Then 1, 1, then 1, then 8. And subtraction is 31. Then about 3, right? 24. Then 7, right? So the remainder is 7. Why? Because 8k plus 1, 8k plus r, right? Plugged into this portion is the same as r squared, just r squared. Do you see it? You can easily prove this fact. You can easily prove this fact. Whether we check whether the power is even or odd, right? Whether the power is even or odd. So when you want to check whether the power is even or odd, all we need to do is this type of calculation, mod 2. Why? Because 8k squared, because 64k squared. 64 divided by 2, right? Divide by 8, and then divide by 2 is 0. And then if you multiply this, then it is 16kr. 16kr divided 8 is 2kr. 2kr divided by 2 is 0. So the first two terms in this expansion are gone in mod 2 calculation. Only remaining things are squared term, right? So in this sense, r squared minus 1 and a cat. Because of this reason, when you have 911, you don't have to square 911. You just square the remainder because of this reason, right? 911 is some big number plus 7 squared. Then all you need to do is 7 squared minus 1, and so. And as you can see, if we do this, then because of this reason, this is equal to minus 1 to the power of 7 squared minus 1 over 8. And the next number is negative 1. And then 17, after extracting 16, 1 minus 1 over 1 squared minus 1 over 8, right? 8 after extracting 16 because of this 16 plus 1, right? 17 is 16 plus 1. So after extracting 16 and then just 1, then 1 squared, then 0, right? Then 0. Do you see it? Just a moment. I wrote, yes. So, what is it? Because of this, what is it? The right side is 1. The left portion is 49 minus 1 is 48, right? 48 divided by 8 is 6. It's positive, right? So positive, so it's 1. So in the end, we got the result. I didn't set this up, right? It's not a setup. You pick the number, I calculate. Of course, I didn't cover all the involved theorems, but at least I gave you the idea why we will study some strange theoretical things.
Is there a reason why you keep shifting from 4k plus 1 to 8k plus 1?
Nothing special. When we develop, then we encounter possible primes. When you handle possible odd primes mean like 2k plus 1 type. But 2k plus 1 does not distinguish very well. Then 2k plus doesn't work well. Then we can consider 4k plus odd number, 1 or 3, or 8k plus odd number, then plus 1, plus 3, or minus 1, minus 3, something like that.
So instead of using 2k plus 1, you're using
Larger number to refine. If we just use 2k plus 1, then sometimes it's true, sometimes it's not. It's very cumbersome. But if we break up, well, like 4k plus 1, then we can break up. But in 2 cases, it's not possible. It's not even possible. Then we can use 8k plus 1. Yes?
So if you use 4k plus r, it's about the same as
4k plus 1 is not the same. I will show you. So take a look. 4k plus r squared, right, equals 4 times 4, 16k squared plus 8 times kr plus r squared, right? So if you divide this by 8, right? If you divide this by 8, 2k squared plus kr plus r squared. With mod 2, this is gone, right? With mod 2, this is gone because of 2, right? But with mod 2, we cannot get rid of this portion. So it's not necessarily r squared. It depends on r, right? So it doesn't necessarily have that property.
You kind of have to know what your number is on where you want to go and whether you use 4k plus r.
Only two cases. As you can see, when you have minus sign, I wrote it before, right? So only 2 cases. Then summary. So when you have odd, right? Odd number, right? Above odd, then no problem, right? Then no problem. Use reciprocity, right? When you have even, right? Then we can break out even, right? So as many evens are written here, right? But even number is only 2, right? Do you see other even number than multiple of 2? So all evens are multiple of 2, right? So you can just take out as many 2's as possible. Then the remainder is odd. Do you see it? So, in essence, when you have even, then you can take out this kind of number as many times as possible, then others are odd. In other words, it falls into this category. Then finally, it has -1 and this. Right? There are 3 possible cases. Take a look. If you find cases other than this, ask. So when you have odd over something, then use reciprocity, right? When you have even over something, then take out as many even numbers as possible and make possible powers, right? When you have negative, then you can have this, right? You can take out the negative. Then only 2 cases. When it has even, right? So when it has even 2 over p, then it is -1 to the power of p squared minus 1 over a. When you have -1 over p, then it has -1 to the power of p minus 1 over 4. Done, right? Only 2 cases, 2 and negative. So this is the full summary of, in some sense, the whole chapter. So why do I mention this? Because from this point on, I will do tedious proof after proof after proof up to the reciprocity. Then you may wonder why the instructor is covering these strange, hard proofs. The goal is having this summary, right? Having this kind of nice properties that we can use in the calculation. On the final exam, I may give you the example like the one that he chose, right? 911 over 2903. Find it. Of course, you can say 1 or -1. Even if your answer is correct, you can get maybe 1% of the allotted point, right? You should show the reason, right? You show the reason why it is 1 or -1. Then, roughly this is if you have odd top portion, then you can use reciprocity, right? If you have even top portion, then you can take out even numbers. If you have negative, then you can take out negative. That's it. So by taking out odd, even, and this, we can continue these steps over and over again until we have found the solution. So I will pause, and then you can browse the summary part and then ask questions. If you don't, then I will continue. Because this is the end of overview, and then I will focus on proof after proof after proof, maybe about almost 7 consecutive proofs. So let's do it. First of all, Theorem 9.3. Theorem 9.3 uses this fact. So we proved this, right? We proved this. In short, if we write it, it is too long. So in short, we can write this way. So formula is easier to treat. Formula is easier to handle, right? So where is this property? So the theorem says this. There are infinitely many primes of this type. So this is the theorem. There are infinitely many primes of this type. Many, just not numbers. Of course, there are infinitely many numbers of this type, but there are infinitely many prime numbers, right? Or primes of this type. This is the one we want to prove. Then what do we do? The first lesson, proof by contradiction, right? Assume not. Assume not. In other words, assume that in this poem we have only these many prime numbers. There are only finitely many prime numbers up to this point, right? So these are all possible prime numbers of this pattern. In other words, we don't have any more prime number than this. And proof by contradiction is the idea. But if you don't understand, ask me. So if not, assume not means what? Assume not means assume that there are only, these are the only possible primes of the pattern of the given form 4 multiplied by something plus 1. So we will assume that this is it. We don't have any more prime numbers of this pattern than just P1 through Pn. N could be very large. Assume that N could be 1 trillion. Doesn't matter. No matter what the N is, we have only finitely many numbers. Then we will contradict this assumption, meaning this is wrong assumption. In other words, there are infinitely many primes. So to do it, now I will create a number. My new number can be called Q. So Q is equal to product of all these numbers, P1, P2, and then I want to make this pattern. How can I make this pattern? Oh, I will multiply 2 and then square. Or I can pull this out, then 4 times this, right? Plus 1. So consider this number, Q. Q is the product of all primes of the form here. So this form is multiplied here and then squared with 2. Then my claim is Q is prime. If my claim is Q is prime, then Q is automatically of what pattern? Q is 4 times some number plus 1 pattern, right? In other words, I create a prime that doesn't belong to the set. That's what I want to do. So I will, instead of claiming it, I will contradict my claim. In other words, I will assume that Q is not prime. So let's go to the next column. So assume that Q is not prime. In other words, assume that Q is divided by an odd prime. P. This is Q is odd, so assume that Q is divided by prime because it's odd number. Even cannot divide, so it's an odd, right? It's odd prime. So let's call that divisor P. Do you follow me? If it is already prime, then we are done. But assume that Q is not prime. Then what happens? P divides Q. And as you can see, because P divides Q, P divides Q can be written with congruence. How can you write this in congruence equation or relation? So please find the way to write this in congruence relation. Q is divided by P can be written in what form? Very basic of congruence, beginning of congruence. Q is divided by P is the same as saying what? Q is congruent what? Mod P. Q is divided by P is the same as Q is congruent what? Mod P? 0. Right? These are equivalent, right? Very big, basic thing. Very basic. So what does this mean? It means Q in the definition, Q is nothing but like 2P1 up to Pn multiplied squared plus 1 is congruent to 0, right? So if we call the portion here x, then x squared plus 1 is congruent to 0. If we subtract 1 from both sides, then it is x squared negative 1. Right? If you don't understand, ask me. It's very basic part of congruence definition. Then, as you can see, this means there is a solution to the above problem, right? Then I can convert this, say, right? Do you understand what I mean or not? If you don't, ask me. In other words, the quadratic equation has a solution. Say this number, right? This number is a solution to this problem mod P. Then we can write the Legendre symbol of this statement. If we use the Legendre symbol of this statement, what is it? If we convert this to Legendre symbol, what is it? Minus 1 over P is what? If we convert this cumbersome long statement by just one symbol, then what is it? This is equivalent to saying what? This is equal to 1. If you don't understand, ask. Then, as I mentioned before, when does the number equal to 1? It is 4k plus 1, right? When P is 4k plus 1, right? When P is 4k plus 1 type, then it is 1. I did it before, right? That means the divisor is 4k plus 1 type, right? The divisor divides it, right? This P is 4k plus 1 type, divides Q. We collected all 4k plus 1 type in the set P1 through Pn. So what does this mean? It means this number P, which is a divisor of Q, is some PR, right? So this P is some PR between P1 through Pn, right? In other words, P which is a divisor of Q is some number between P1 through Pn. Something, because we have only finitely many of this type. This means what? Take a look. PR divides both Q, right? Right? PR divides both Q and then PR. Right? P divides both Q and PR. Because it divides PR, any multiple of PR can be divided. In other words, PR times P1, P2, all the way up to Pn other than PR. So we can just put this PR in, and then even 2. So PR divides these two numbers. Do you see it or not? PR divides both Q and this. Where was this fact? I said this. In the first position, I wrote it, right? Assume that Q is divided by P happen to be PR, right? So P divides Q. And PR is here, so PR divides this product. So it divides two numbers, then it divides the difference. In other words, PR divides Q minus 2 P1, P2 up to Pn. Even if it divides, then it divides square. What is this number? 1, right? So PR divides 1. Is it possible? Right? Bigger number divides smaller number? Impossible. So contradiction. In other words, there are infinitely many prime numbers of the form 4k plus 1, right? So this is the proof. So stating is easy, proving is not. So very, very small and little thing is required in the proof. As I mentioned before, this course is not addition or multiplication, no. It's about proof. But on the final exam, I will reduce the proof problem to like 1 or 2, right? because I realized that it could be a disaster to many people. I try to avoid the problem. Even if you ask, I may ask shorter questions. So take a look and then ask questions. But as you can see, even one proof requires the whole hour. And I don't want to cover too many cases today. Next time, I will cover more. But I already overviewed all the way up to the end, right? So let's stop here. And if you have a question, you can approach and ask.